Okay, good afternoon, everybody. So, in this lecture, we are going to learn about a property of a function, namely function of bounded variation. So, here we are pronouncing the term variation. Variation, you can think that it is a measurement along y-axis. So, you have to ignore the measurement along x-axis. So, if you are moving on a curve, so you have to count that measurement along y-axis. Now on a certain interval, if that variation, the sum of the variations is finite, then the function is said to have a bounded variation on that interval. So it is not a property that you can say the curve is bounded variation throughout any interval. So for a specific interval you can say, and for example if you are considering about constant function, so its variation is 0, and that's why it has a total variation of 0. And if you are thinking of a function like y equal to x, and in that case the total variation will be what, f of b minus f of a, that is suppose you are considering the interval 2 4, then the variation is 4 minus 2, that means f of b minus f of a here. And similar way, if you are considering the function for a step function, then it has the similar property, and it will have also the total variation as f of b minus f of a. Now there are some questions you can ask, that a continuous function and bounded variation, is there any relation? Or a function which has derivative, is it bounded variation? Or what about the function like x sin x, x sin 1 by x, and sin 1 by x, like this? So we will discuss about this. So before that, formally we have to know the definition of bounded variation in a formal way. So okay, yes, the formal definition, if you think, okay, now formally you have to define a function from an interval to another codomain, and it is assumed r here. So if ab to r is a function, and have assumed a partition x0, x1, xn, and xnp here. So with this partition we are measuring the differences between the two consecutive points. So f of xi plus 1 minus f of xi, that is the functional values at two consecutive points and their difference, absolute value, and so on for the whole interval, for with the help of that partition 1 to np 0 to np minus 1, sorry. And for a particular partition you will get a value, and if you change the partition, you can refine the partition, you can add 1 point to that partition, and after that you will have a set of points of that partitions. So if you take that supremum, if you take take the supremum of the set of all such sums, then that value, if it is finite, then you can say that the function is of bounded variation, and this total, that is this supremum, is called total variation. Okay, so this definition is quite easy, and you can understand the whole analysis Now here another definition, another way it can be proved that a real function f is bounded variation in AB if and only if it can be written as the difference of two non-decreasing function, and this result is okay. So our next step is to describe some properties. So first property, you can say that a function of bounded variation has only jump discontinuity or removable discontinuities. So this is an important property of function of bounded variation what we have asked earlier in this lecture, that what is the relation between continuity and bounded variation. So a continuous function may not be a function of bounded variation, but it has a certain property that if the function is discontinuous, the discontinuities may be of removable type. That means both limit exist may be equal but not equal to that functional value, or the limits are different, that is left limit or right limit are different. So this kind of scenario will exist if the function is of bounded variation. Okay, so another okay, here is an example, sine 1 by x. As you know, this function is not continuous, not even bounded variation. So in the interval 0 to 2, 2 by pi. So if you change the interval, that is from a to b, where a greater than 0, the function is of bounded variation. So it is clearly to be mentioned that at the point 0, the variation is can't be a measure in the interval of 0, in the neighborhood of 0, as you see in the picture. Now another function is x sine 1 by x, and in that case this function is continuous. This function is continuous and bounded also, but this function is also not a bounded variation, as it does not exist. This figure is little bit changed because of that x. So y equal to x, if you draw the line y equal to x and y equal to minus x, so the variation will be lying between these two lines. Okay, so another function we are talking about, and the function is fx equal to 0 when x equal to 0, and fx equal to x square sine 1 by x if x not equal to 0. So clearly the function is defined here at 0, and this function is of bounded variation in the interval 0 to 2 by pi because of its curved nature. So you can check that the curve is like flat curve at 0, and in any interval the variation can be measured. So some properties, you can say that function of bounded variation have been studied in connection with the set of discontinuities of function and differentiability of real function. The following results are well known. If f is real function of bounded variation on AP, then f is continuous except at most countable set, and f has one-sided limits everywhere. Limits from left side in AB semi-open, from right side AB semi-open. The derivative exists almost everywhere except of a set of measured 0. Now at last we are going to discuss an example which is not a bounded variation. So I mentioned some function earlier about this. Here is another example, that 1 by x. So 1 by x, this function is also an example of not bounded variation between the interval or in the interval 0 to 1. Now another example, this is also discussed, similar function is also discussed earlier. This function is sin pi by x. The function is bounded, as you know, the value of sin x lie between 0 to 1. In that case, this is bounded function but not a bounded variation. Continuous function, as discussed earlier, x sin pi by x, it is a continuous function and still it is not a function of bounded variation. Okay, so lastly we can conclude that what about a function which is continuous or uniformly continuous. What about this function? So here we can only say about Lipschitz function. So Lipschitz function is your bounded variation, and you can see that Lipschitz function follows the property f of x minus f of y, which is k times less than x minus y. So if you put any functions, two consecutive values, and that value will be k times xi minus xi minus 1, and ultimately the result will be k into b minus a. So that means it is finite, and so for every partition the value will be finite, and hence the function is a bounded variation. So Lipschitz function is a bounded variation, and monotonic functions are also a function of bounded variation. As you know, you can check it with the after the definition. So and few properties are will be discussed in later class with the proofs of these statements what we have claimed here. Okay, thank you very much till now.